Sorry for the tardy start, but we can cover everything. Today, I'm talking about unanswered questions in cosmology, which I'll remind you is the study of the structure of the universe. And before we get too far into it, let me explain what's currently understood about the past and future of our universe, and that's illustrated here. On the left, there's a kind of a bright white area. That's what we commonly refer to as the Big Bang. Lots is understood about this region of time. That is, we have a self-consistent set of theories about creation of elements in the early universe, how the universe evolved, how galaxies evolved, and this Big Bang was followed by a dramatic increase in the size of the universe, and we'll talk about what size means in a second. And then the universe evolved for about 13.7 billion years. This is the nearest 3 billion light years to Earth. Each little yellow dot is not a star, it's a galaxy. And each galaxy has perhaps 100 million or up to 10 billion stars in it. So lots of stars out there. And the interesting part of this is, you see this structure here. There's a cluster of galaxies about the same, and we're here. There's a cluster of galaxies around us. And then there's a void. This is a repeating theme. Then there's a bunch of galaxies here, and there's a void. And then there's a dense group here, and then much fewer galaxies. Out here, we don't see many galaxies because they're just that much farther away, and they're hard to detect. Here's our galaxy, the Milky Way. It takes 230 million years for our galaxy to rotate one time. We're 27,000 light years from the center, and we're going 800,000 kilometers per hour around the center of the galaxy. So motion is complicated when you introduce the motion of Earth around the sun in the galaxy. The galaxy is also moving relative to its neighbors and so forth. So the upshot of this is how many stars are in the universe. 10 to the 11th galaxies, that's a 10 followed by 11 zero, or 1 followed by 11 zeros. And then each of those has 10 to the 11th stars, so there should be 22 zeros there. That's more stars than there are grains of sand on the planet. So here's a first, now I'm talking about dilemmas that we've encountered and they remain unresolved. So before the expansion of the universe was discovered in the 1920s, Einstein and a few others had this idea that the universe was static, that everything around us was there from the beginning and nothing was moving. This includes my namesake, Friedman with two N's. That's Alexander Friedman from the Soviet, or what became the Soviet, or it was the Soviet Union. And this is a Belgian priest, Lemaitre. Both of them understood Einstein's equations well enough to calculate what the possible futures might be. And I'll show you that in a second. And there's some technical details here. Here are the possible futures they saw. One is that if we're here now, the universe could expand and then contract, and we would have what is sometimes called a big crunch, and all life would be snuffed out. And then maybe this involved a bounce. That is, the universe would expand and contract, and then possibly re-expand and recontract. There's another possible universe that expands ever so slightly forever. Then there's one that expands and keeps growing. That is, the rate of expansion keeps getting bigger. And then this one was considered to be the least likely. where the expansion accelerates. That is, we have expansion that just runs away. Kind of like if you have a microphone near a speaker and you hear that screech. That screech would be the expansion of the universe so rapidly that stars would run away from each other and we would never have galaxies and the structure of the universe we see today. So this red one was considered to be the least likely. These were considered to be possible. This one looks pretty dangerous because the universe gets big and then collapses to a point. The first measurements to confirm what is really happening came from Edwin Hubble, this person, who working in the mid-1920s demonstrated that the universe was actually expanding and the objects, galaxies farthest away from us were receding from us at the highest rates. This was a big surprise, particularly to Einstein. He was quite surprised that the equations which predicted possible expansion actually worked with observed astronomical data. And here's how the expansion works. If we have a universe that's this big and there are two objects sitting on the surface of that universe, over a period of time, if the universe gets bigger, those objects get farther apart even if they're not moving. So here's one way to illustrate it. I want to show you this little cartoon I made. So two ships at sea, you measure the distance between them. Even if they're not moving through the water, if Earth's radius is getting bigger, they get farther apart, even if they're not moving, because everything would get stretched. And a common question at this point is, what's outside the universe? And the way to answer that is to look once again at this surface. The only reason we can see these points on this surface spreading apart from one another is we have a vantage point of a higher dimension. So imagine these are ants on this surface of a sphere, and the sphere is getting larger. That is, its radius is getting larger. The ants will see each other receding. Even if the ants aren't moving, they'll see their neighbors, all their neighbors going away from them, and there's no special point. Every ant on this surface will see all their neighbors receding from them simply because the object is getting bigger. What is the concept of outside for the ants? They're confined to the surface of a sphere. They don't have a sense of up or down. They only have a two-dimensional experience. So the only way to really see how our universe expanding can work is if we had a vantage point with one higher dimension, so we could look at the three-dimensional experience that we have. Our universe is three spatial dimensions, but to see its expansion means thinking in terms of another dimension. Just like it takes three dimensions to see the expansion of this surface on which ants are streaming away from one another. But between the time of Hubble in 1920s until very recently, the expansion rate was thought to be such that the universe was just slowly drifting apart. But I've animated this. The blue area of this curve, and you can see almost all the measurements are in the blue area. This says the universe is actually accelerating in its expansion rate. So let's go back to the curve I showed you earlier, the speculations of Friedman and his colleagues. This one was considered to be the least likely possible future for the universe, but it turns out that's the actual future of the universe. None of this made sense. It's a complete surprise. And it's a essentially unresolved issue, except we know by multiple different kinds of measurements that our universe is not only expanding, the rate of expansion is accelerating. And there's a reason why, which we will talk, and see this little character here, he's a scientist who's totally surprised by this outcome. So now we've had that introduction. Let's talk about some unresolved issues related to the structure of our universe. And rather than show you the list here, let's just get into it because I missed the first few minutes. The stuff we are made of, atoms, and the stuff that stars are made of and galaxies, all of that, it turns out, represents 5% of what's in the universe. This is a recent development. This is emerged over the last 30 years. The best way to show it is this pie chart. This sliver here, that's all the stars and galaxies and stuff we're made of. The rest of it is made up of two types of unknown material. This is called dark matter. We see this as evidenced by the way galaxies behave. And right now we have no explanation for that way the galaxies behave. I'll show you what I mean in a second. But about a fourth of the universe is made up of something called dark matter. We don't know what it is. We don't know how to find it. The rest of the universe, 68 to 70%, is dark energy. This is also a mysterious kind of stuff. And what it does is, as the universe expands, dark energy jumps in and fills that vacuum and adds in more energy, which accelerates the expansion of the universe. And as the universe expands, more dark energy fills that void. And so we end up with an accelerating universe. So we do have an explanation of sorts that this mysterious stuff, dark energy, is fueling the accelerating expansion of the universe. What it is, we do not know. We have something that we can hang our hat on. It's called concordance. Multiple different astronomical methods of measurement are used to try to confirm that the two numbers for dark energy and dark matter that I just showed you are actually true. So if we study supernova events, that is explosions of stars, they tell us that the mixture of dark matter is this scale, dark energy is this. The supernova events confine the universe to this set of blue ellipses. If we look at something called a cosmic microwave background, which is a completely different way to measure the universe, those results say that everything in the universe is confined to this kind of blade-shaped orange area. If we look at the acoustic oscillations in the early universe, yet another independent way to look at it, we get this green area. And they all converge on this little area right here. And if you look closely over here, we get that the dark energy of the universe is confined to a number like 70%, which is what I just showed you on that pie chart. And at the same time, the matter density of the universe is about 30%. So let's go back and look at the pie chart. There it is. So if you add these two pieces, the 5% of stuff we're made of, to the dark matter, you get about 32%. And if you look at the dark energy, you get 68%. So the concordance of multiple types of independent measurements force us to think in terms of that pie chart. This is, as I say, new information developed over the last 30 years or so. And a big chunk of the universe, 95% of it, is unknown to us. We just don't know what it is. There's another way to look at this too, and that is to look at the abundance of different elements in the universe. Astronomers are very good at doing this. They look at a galaxy and they can tell how much of that galaxy is lithium, iron, sodium, mercury, and so forth. And they have theories confirmed in a variety of different ways for how elements were formed in the early universe, in the Big Bang. The universe has a knob we can turn. And that knob is how much of the universe is the stuff we're made of. How much of it is made of atoms. And if we turn that knob until the theory matches the measurements for how much deuterium is in the universe, or lithium, or helium, when we turn that knob until we get the best match for all the observations we make about what's in galaxies, it says the amount of matter made of atoms is about 4 to 5%. That confirms the pie chart as well. Remember, we said 5% of the universe is the stuff we're made of. The rest of it is a complete mystery. So that's one unresolved issue that really includes two things. What is dark matter made of, and what is dark energy made of? And people are scrambling to figure this out. The next issue I want to describe is the geometry of the universe. And I want to point out with this little video that there's a difference between geometry and shape. Most of us would look at this flat surface here. It looks like a checkerboard. We would say that has a flat shape and is different than this torus or bagel-shaped surface, when in fact, see the little faces are running around. It turns out that there's a way to show that this flat surface is actually the same as the torus. So we'll show this a couple times so you see this. If we take a flat sheet of paper and roll it into a tube like that, that still has a flat geometry. And if we then bend that tube and join the ends of the tube, we get something that looks like a bagel. And that has a flat geometry, but it does not have a flat shape. So that's a subtle difference between what we mean when we're talking about shape and geometry. And the key question here is, what is the geometry of the universe? This is open to speculation, as is the parallel question is the universe infinite in size or finite in size? Both of these questions are under constant scrutiny by theorists and astronomers who make measurements. That's a still unresolved issue. So we've made the point that flat geometry and a flat shape can look different to us. One way to dictate or define different types of geometries is to draw triangles. If you take all of us learned this in high school geometry, if you take a flat surface and draw a triangle, that triangle contains 180 degrees. If you then take something that looks like a saddle you put on a horse and draw a triangle, this triangle has less than 180 degrees. And if you take an example we all know from latitude and longitude on the globe, if you draw a triangle of this type, you can have a right triangle at the North Pole and a right triangle at the equator and another right triangle at the equator. So here we have a triangle, a spherical triangle, that has 270 degrees. So one way that astronomers attack the question of the geometry of the universe is to look at how shapes appear. Do we see 180 degrees, less than 180, or greater than 180 in triangles? That is, attempting to understand how straight lines intersecting fall on one of these surfaces. It's a difficult thing to work on, and that's why this remains an unresolved issue. I've already mentioned something called the cosmic microwave background. This is the result of the very early radiation produced in the universe. We've measured it many, many times, both from the ground and in space. And the picture right now that we have that matches best between what we measure in the microwave background and the theory of the geometry of the universe is this patch right here, which is associated with a flat geometry. And up until a few months ago, everybody was pretty confident that the universe has a flat geometry. The actual shape is unknown, could be a torus or something else. And the reason I mention a few months is there's now all of a sudden some new data has emerged suggesting that the universe isn't quite as flat as we thought. It might be closed. That is, it might have a shape more like a sphere. This remains one of the things I've put on the list, an unresolved issue in our understanding of cosmology. The arrow indicates where we were, say, in June of this year. High confidence that the universe had a flat geometry and some unknown shape. Now we're not so sure. I mentioned dark energy, so here's a summary of what we know about energy in the universe. This set of four things, that's planets, stars, somewhere in here is us. If you group those together, that represents 5% of the matter and energy in the universe. Dark matter, 25%, dark energy, 70%, but nobody knows what the dark energy is. There is a Nobel Prize awarded in 2011 for the acceleration of the universe to Rice, Perlmutter, and Schmidt. Their works revealed the accelerating universe. Now everybody's scrambling to make sure we understand why the acceleration occurs and where's the dark energy that fuels the acceleration, where's that coming from? Here's another little issue. I already mentioned Edwin Hubble. He's the one that found the expansion of the universe back in the 1920s. Now, let me show you the graph. And notice here, I'm plotting estimates of the Hubble constant. That's a number we assign to the expansion rate. Here's a graph I'm going to show you that ranges from over the last 20 years or so, measuring the Hubble constant a lot of different ways. I've listed some of them there. And you see, back in around 2000, we had estimates of the Hubble constant. It's a number that ranges from 65 to 80 in some special units. But back in 2000, we had two independent ways to measure the Hubble constant. And they overlapped, and everybody was happy because the presumption was that if we refine our data, we'll find that multiple independent ways of measuring the Hubble constant will all give us the same number. But look what happened by about 2013. The data, the vertical here shows the uncertainty about the measurements. So the technique using what are called Cepheid variable stars, that got better and better along the way. And gradually, by 2013, we could see it's not giving the same result as the cosmic microwave background. And then a third technique has been introduced recently, and it unhappily falls right between the two. So the best estimate for the Hubble constant for Cepheid variables is here. The best estimate currently from cosmic microwave background is here. And this third technique, which was hoped was going to resolve the issue, hasn't resolved it. It lies right in the middle. So Hubble constant remains uncertain. And the interesting thing about the Hubble constant is if you invert it and do some arithmetic, it tells you the age of the universe. So if we don't know the Hubble constant, we don't know the age of the universe. That's problematic. Dark matter, I mentioned, is related to galaxy dynamics. Let me do something here. This is an informal group. I'm going to shed my tie, if I can, without strangling myself. This is a result of eating too much on the boat, right? Everything about me has gotten bloated. So here's an interesting thing about galaxies. When we measure the motion of stars in our galaxy, we expect to get something that looks like this, A. We don't. We get something that looks like B. This was discovered in the early 50s. It remains unresolved And it leads to the implication that there is something we are now calling dark matter. Dark matter is of unknown origin. If we invoke dark matter, we can explain this behavior of the galaxies. But it still remains, we just changed one mystery for another. The anthropic principle. This is an unresolved issue, and it has to do with how is it that we are here to observe this universe? The universe is old, it's large. We know life exists in at least one spot, namely here, and we're intelligent enough to observe the universe. The question is the universe designed so that we can evolve and make the observations? Or are there multiple universes with different laws, some of which are observable and some which are not? And that implies, or invokes, the question of fine-tuning. Was the universe designed to be a hospitable place for us? Or is it just an accident that we're able to evolve and make these observations? Let me take a little break here. I'm having a little experience from the ship's motion. Let me take a seat here. While I'm sitting, are there questions about what I've said so far? Yes? Well, we detect the expansion using the Doppler effect. Yes, so we see galaxies appear red. So we have lots of information about the spectra of elements like hydrogen and helium. When we look at receding galaxies, we see the fingerprint of helium or hydrogen, except it's shifted in the red. So you're right. But that's the technique we use to detect the expansion. It doesn't explain why the expansion is what it is. Let me do something here. So there's a lot of debate about why the universe is expanding the way it is and whether the universe is fine-tuned for us. And that leads to the issue of what are called multiverses, where we now have a universe, not just the one we live in, but a collection of universes that are isolated from one another, and that there may be an infinite number of such universes, each with its own laws of physics, its own rate of potential evolution of intelligent beings, or there may be an infinite number of universes that are hostile to life. Remember, I said if the expansion rate of our universe was much bigger than it is, we'd never have stars form, and that would end the possibility of humans evolving. Or we could have had an expansion rate that allowed stars to form, but galaxies not form. And galaxies are critical because when stars consume their energy, just like our sun will eventually, that star will implode if it's big enough, and it will cease to be a part of the universe. It might become a black hole. But the critical thing is that galaxies reuse the debris from dead stars and produce new stars. And our Milky Way has areas in it which are highly efficient at producing new stars. So if the universe's expansion was high enough that galaxies didn't form, all the stars that happen to be created would eventually burn out and the universe would be totally dark. It would just be clouds of gas and dust and gradually just become more and more dilute. So this idea of multiverses, this is a relatively new idea, and it implies that there might be an infinite number of different universes, possibly with the same physics laws that we enjoy or not. And so we've all played this game. There's two cartoons here. We could be representing two universes of galaxies. And you have to look very closely to see what the difference is. And I'll give you an example of what I'm talking about. Suppose somewhere in this multiverse, there's another universe that allows life. And because there's possibly an infinite number of such universes, there might be one where there's a ship, very much like this one, traveling in an ocean very much like where we are now. Everything the same, except a dog walks in right now. And I'm waiting to see if the dog, no. Because anytime you have an infinite number of things, anything's possible. And in another version, Brad Pitt is giving this lecture, not me. Here's another mystery that's unresolved. There is, in atomic physics, the idea of antimatter. That is, it's matter that is sort of a mirror reflection of the matter, the atoms and so forth that we're made of. And the presumption is all the antimatter that might have been created in the early universe found a partner, like an electron and its anti-electron, called a positron. When they meet, there's a little flash of light, and those two particles are gone and get converted into a flash of light. Our universe, we look everywhere. We can't find any antimatter. We can make it in the laboratory, so we know it's real stuff. But when we look at galaxies, there's no evidence that there are galaxies made of antimatter. So the question is, why is there the stuff we call matter, the stuff we're made of? Where's the antimatter? If it has all canceled out with, like I mentioned, electron and its antimatter particle, why is there any matter in the universe at all? So there's an unexplained question. How is it that the universe had more matter than antimatter in the early days, and all the antimatter is now gone? No one can explain that. So we started a little late, and I think we probably ended a few minutes early, but this is the end of this lecture. It poses questions that you might want to follow up on if you're curious enough about this to have attended this lecture. Just keep checking the science news. You're going to see speculation and resolution over the next few decades of some of these questions. Some of these questions are not going to ever be resolved. So with that, I thank you for indulging me, letting me sit down during this lecture. And if there are questions, I'll be happy to entertain them. And thanks for listening.